We have a long history of people making phenological observations, usually as a practical tool to better time agricultural activities, wildlife watching, and food gathering activities. Phenology and phenological observations are also of great value in helping us better understand the effects of climate change. I am Paul Alabak, a scientist with Project Budburst. In this video, I will introduce the concept of climate change and how it applies to Project Budburst. The next video will then provide more detail about how Project Budburst data can be used to better understand climate change and adaptation to climate change. First, we need a little background on climate. Weather is often confused with climate. You could say that climate is what you're supposed to have, and weather is what you get. So climate change has to do with changing average weather conditions, not necessarily changing the weather on any given day. One useful way of thinking about this is to look at the current pattern of weather variability. We know all too well how variable our weather can be from year to year. Climate change should result in changing average weather conditions in any given place. For example, if there is a 10-degree warming in Baltimore, what are now considered the warmest days will become average days in the future. This is particularly true of winter and early spring seasons, where temperature has the greatest effect on plant phenology. The second aspect that climate change is likely to affect is the frequency of extreme weather events, such as heat waves, tornadoes, droughts, and flooding events. For plants, it is often these extremes that may lead to species disappearing from old habitats. In this example, you can see that the average number of days over 90 degrees Fahrenheit each year in the southeast is expected to triple by the end of the century. One of the most difficult aspects of learning about climate change is trying to understand how you can translate changes in global climate to the actual weather conditions you should expect in a specific local place. For example, during the 20th century, the Earth has warmed about 0.6 degrees Celsius, which seems like a really tiny amount. But this is an average all over the Earth, so some areas have warmed a lot and others may have changed little or even have become cooler. In the Midwestern and Eastern United States, as an example, dramatic changes in forest trees are predicted to occur by the end of the century. The northern beech maple forests are predicted to be replaced by oak and pine forests. These regional differences are important to understand. This is why Project Budburst, as a nationwide program, has a critical role to play in documenting these changes. Phenology is a very useful general indicator of how our natural environment is changing. Phenology is very sensitive to even subtle changes in weather or climate, as we explained in our first video on what is phenology. Plants use environmental cues to determine when to start growing in the spring or when to become dormant in the summer or the fall. These cues are often related to day length, temperature, or rainfall. Most studies of plant phenology have found a particularly strong relationship between temperature and the timing of plant events or phenophases, such as when leaves emerge and when the first flowers appear. If you increase average temperatures, then plants should flower earlier. In this example, apricot trees flower 10 days earlier for every 2-degree increase in average temperature. In fact, we have seen all over the Northern Hemisphere that plants are flowering earlier. Here is an example from Chicago where data collected from 1954 to 1994 were compared to data collected by Project Budburst volunteers from 2007 to 2009. This shows that plants are flowering an average of 10 to 20 days earlier than they did historically. So why is this earlier flowering important? It sounds great to gardeners and agriculturists. In fact, in just the past 20 years, the northern parts of our country have so dramatically changed their winter climate that you now can grow many plant species hundreds of miles north of where they used to suffer from frost or extreme winter storms in the past. One good example of the challenge for plants or animals experiencing phenological effects of climate change is the pied flycatcher in Europe. These migratory birds generally arrive in the spring when their critical food source, caterpillars, are abundant on new oak leaves. In recent decades, the climate has become much warmer, especially in the winter and spring, so oak trees are sending out leaves on an average of 2 weeks earlier. Caterpillars, the food source for the migrating flycatchers, are emerging early as well. But the pied flycatcher still arrives at the same time each year because its migratory cue is day length, not temperature. For pied flycatchers, earlier warming temperatures do not signal earlier migration. This is what ecologists call a mismatch. The birds and their food source, the caterpillars, are using different environmental cues to determine their phenology. So now the birds are no longer arriving when the caterpillars are most abundant, and bird populations are now declining. Once we have enough data, scientists will be able to use the information to better understand how the environment is changing and how relationships between species will change. These data and your observations about these changes are of critical importance as cities, counties, states, and regions try to make informed decisions about how to better adapt to climate change and better understand which species in which regions will be at the greatest risk. Thanks for listening. To learn more about why Project Redburst is important to science, please view other videos.